the project on comprehensive resilience building in the Chimanimani and Chipinge districts, which is funded through the World Bank and supported and managed through UNOPS. So in this context, we have been working with Deltares, and we have been identifying a way forward to identify the flood hazards in the area of Chimani Chipinge in collaboration with a spin-off of the University of Bristol in the UK called FATM. And based on that information, we have invited Deltares to move towards a exposure assessment of assets in the area related to flood risk. So in this session, we will go a bit more in detail, and as a final activity of this collaboration with Deltares, they will provide a presentation of flood risks in general, the role of exposure and vulnerability analyses, but also the concept of Delft Fiat, the open source online tool that can be used free of charge for developing flood assessments. And then, of course, there is a demo on how to use Delft Fiat, and then the case study from Chipinge and Chimanimani area are used to demonstrate it. After that, I would like to have a discussion about how these results can be used in Chipinge and Chimanimani, but also what are the limitations and opportunities for further work, and what additional information could help the audience in follow-up activities, and how can we upscale the use of this type of tools in the larger areas of interest. So I think without further delay, I will just introduce the two speakers. So the first colleague here is Dr. Ferdinand Dirmanse. He's a senior specialist at Deltares, Netherlands, with an MSc in applied mathematics and a PhD in hydrology, both from the University of Delft of Technology. And he's, of course, an expert in the field of flood risk management analyses. Over the last 20 years, he has amassed a lot of work in this field. We also count with Dr. Bramka Giaffino, and he's an advisor at Deltares currently, and he's working also on supporting flood risk management through quantitative models with an emphasis on promoting equity and fairness in the planning process. His work focuses on simulation models, machine learning techniques to support climate change adaptation and mitigation planning under deep uncertainty. So I just welcome two colleagues. Ferdinand, Bramka, the floor is yours for this session. Thank you.
Thank you, Koen. So indeed, my name is Ferdinand Diermanse. So I will do the first part of this presentation. So my question, first of all, to you is, can you see my screen now?
Yes, please go ahead.
Okay. Okay, so I will start off this presentation. Well, first of all, welcome to you all, and thank you for joining. I will start this presentation talking a little bit about flood risk in general. Take away my sunny window a little bit. And then after that, my colleague Bramka will take over and explain more details about the actual application, and specifically, as Koen told you, about the Delft Fiat application. So how it works, and in the end, we also, of course, will show some results. Okay, so first a little bit of background on the flood risk assessment. Perhaps it's some of you are familiar with this, but I can imagine others are a bit more remote from this topic. So it would be good to start a little bit from scratch in this explaining. So first of all, why do we do this kind of work? Why do we do flood risk analysis, especially within the context of flood risk management? Now, there's a general idea that even though we wish we could prevent floods all the time, this is simply not possible. So there's no country in the world where they can prevent floods with 100% certainty. And that means that flood risk, like other risks as well, are essentially a fact of life. So flood risk management mainly had a main objective of flood risk management is to reduce those risks as much as possible. But it's important to note that you always have to do that within the available resources. And there are a lot of resources relevant. First of all, of course, budget is an important one. We don't have money to to take all the measures that we like. Time is often a resource, and we don't have all the time to do it. Also, available knowledge in general, background knowledge on how physics work, but also even more important, very detailed knowledge on the area itself, like where do the people live, their houses, how are they, can they deal with flooding? That a lot of details are relevant for flood risk analysis, and it takes quite a bit of time and effort to get more information about it. And last but not least, public and political support, because we can think of measures, but some of them will be very disruptive. First of all, because maybe they cost a lot of money, but also they can disrupt society. For instance, if we build a reservoir and we have to move people out of their homes, their villages, because their villages will be flooded, that of course has a huge impact, and that can mean you don't get the support for that. Okay, so then how do we manage those risks? Well, first of all, if you want to reduce the risks, the best thing is to select measures that are most effective, that reduce the risk as much as possible. So that means it's good to have some notion about where the risk is the highest. And then it's good to realize, like, what is risk to begin with. Well, the most simple, straightforward explanation of risk is that it's a combination of likelihood of an event and the impact of an event. And so if you are living in an area where a flood event is very likely to happen, and such an event also often has a very a big impact, that means that you live in a high risk area, because that means that you will quite often be confronted with the impacts of a flood event. So identifying those areas and then identifying where the risk is highest is a first start in to really focus, like, okay, where should we first take the measures? And maybe perhaps not focused on the areas on the lower left shown in this graph, where there's rarely any flooding, and if floods occur, the impacts are very low. Those are the low risk areas. We probably don't need to take measures there. So prioritizing measures based on where the biggest risk can be reduced, that's one vital step. But another one to consider is, like, how cost effective is a measure, and cost can be in a broader sense. And here I show an example that it's not related to flood, but I think it's very appealing and easy to understand. So in the 1970s in the Netherlands and in a lot of other countries as well, we had a lot of casualties from traffic accidents, and then seat belts were introduced. They became obligatory, and that has, in the Netherlands alone, saved hundreds of lives every year ever since. So this is a very and it was a relatively simple measure to take, and not very costly, but relatively easy to implement, with a very big impact. So and that's also good to look at how cost effective is a measure, the low hanging fruit, so to say. That's what you need to look for. So what does that mean? So in the end, when we want to take measures, it's essentially looking at cost effectiveness, but then cost effectiveness in the broadest sense of the word. So I'm not only talking here about dollars or euros, it's really costs in the broader sense. First of all, if we look at costs of measures versus benefits, well, on the cost end, here on the left side, we have, of course, the construction costs and maintenance costs of if you want to build a reservoir or a retention pond or a levee, etc. But additional costs are that you have the societal disruption in some cases, like I mentioned before. You can have environmental impacts. And this is just the start of the list. There can be other costs involved as well. But on the other hand, you also have the benefits of taking measures. And the benefits are in general that by preventing floods, you prevent a lot of costs, such as casualties, people that are affected by floods, environmental impacts. And floods can also cause environmental impacts if the water is contaminated. Damages to assets, like shown in the picture below. The economy is often hampered if you have especially long duration flooding. And reputation loss is also important, because if an area floods quite regularly, then typically people are not willing to invest in such an area. So there is a lot to be gained by taking these measures. And well, the prioritizing or choosing the best measures is really balancing this whole cost-benefit ratio in the broader sense of the word. Now, how do you do that balancing? Well, in order to explain that, I'm going to simplify things a little bit here in this schematic view. So imagine that we only look at costs in terms of dollars and forget the other ones. So what you can do is then take a measure. For instance, you can build a small dam or a bigger dam, and essentially the size that you want to look at, or that represents the level of protection. You can imagine if you build a higher dam, it will give more protection than if you build a relatively low dam. So on this in this graph, I show the level of protection on the horizontal axis, and the costs involved are shown on the vertical axis. Now you can imagine, hey, if you increase the level of protection, you build this higher dam, that means that your investment costs will increase. You need to invest more to make this happen. So that is shown with the red line here. Now, on the other hand, by increasing the level of protection, you reduce the flood risk. So you reduce the expected damages that you get every year from flooding. And that is shown in the green line. So the green line is going down. So we have the investment costs going up with the level of protection, and the expected damages going down with the level of protection. And then if you combine the two, if you take the sum, then you get the blue line here that shows the total costs. So that's the sum of the investment costs and of the expected damages. And there you can see it's kind of a curved line, and that somewhere in the middle, where the dashed line meets, there's an optimum. That's where you have the lowest total costs. And that could be, let's say, sort of the optimum choice, where you have the minimum total costs. So this is just a very schematic view of how you can balance the investment costs on one hand and the benefits on the other hand. But once again, I have to emphasize this is very theoretical. This is just to give you an idea on how you can balance these things. Now, and highlighted here are the expected damages. So if you want to know how those damages, what are on average the damage you have from flooding in the current situation, and how will that change if you increase the level of protection, now that's typically the information that you need, and you get that from doing a flood risk analysis. And that's how you get your information on the flood risk. So that is one of the reasons why we do this type of analysis, to see what is the flood risk and how can we reduce it, which measures will reduce this flood risk. And once again, I keep on emphasizing, in this example, I'm just essentially talking about balancing costs in terms of money, but in general, it's more than just money that we are talking about. Okay, so flood risk. We want to do a flood risk analysis. Now, there are lots of different definitions of risk and flood risk, but the one shown here is in my experience the ones that is currently used in most studies. That is where risk is composed of three different components. It's a combination of the hazard, exposure, and the vulnerability. Now, in the hazard to begin with, the hazard is in this case a combination of the probability and the magnitude of flood events. So how likely is it that a flood will happen in a specific area? And if it happens, what is the size of the area that is flooded? But also how deep will the flood water be? And what is the flood depth? Or what are the flow velocities? Because that can also be of relevance to the damage that will occur. So that is the hazard part of it, the actual flood itself. Then the second part is the exposure. And so that's all the assets and the population at risk. So essentially all the houses and critical infrastructure and the people that live in the floodplains. Because you can imagine if there's a river and nobody is living next to it, there's also no flood risk, because then a flood event is simply a natural phenomenon without any damages and therefore no risk. And so the exposure is also a relevant component in what determines the risk. And then there's the third component, that's the vulnerability. So if a flood event occurs and we have people living in the floodplains and we have those houses and assets, etc., then the vulnerability essentially determines what the actual impact of such a flood event will be. And so the vulnerability is related to, for instance, are the houses flood proof? And so if a flood occurs but a house is totally waterproof, then there won't be much damage to that house. But it's also related to the people. If a flood occurs, are they warned in time by a flood warning? And if they are warned, do they know how to act? Do they know where to go to, where to evacuate to? And also, do they have enough time to put their valuable stuff on the highest floor, or to pack their valuable stuff and bring it along with them when they go to higher grounds? So those are all aspects that determine the vulnerability. And so the combination of those three aspects determines the total risk. And therefore, in the flood risk analysis, what we do is we analyze all three of these components and then see what the flood risk is. Now, quite often you also see this division where instead of hazard, exposure, vulnerability, the analysis is essentially split in two, where on one hand flood hazard is analyzed, and on the other hand the flood impact is analyzed. So that's essentially a combination of the magnitude of the event, the exposure, and the vulnerability. Now, why do I show this today? Well, that's to put things in place, and especially the Delft Fiat tool that my colleague Bramka will be explaining later on. So the Delft Fiat tool is all about analyzing the flood impact. So everything on the right side of this picture. And on the left side of this picture, the flood hazard, that's a separate analysis. And for this particular project, that was also carried out by a different institute than Deltares. It's called FAT. So this slide I just showed to introduce those terms like flood impact, so that it's clear what is happening in this Delft Fiat tool and what is happening outside of this Delft Fiat tool. Now, back to the hazard, exposure, and vulnerability. The nice thing about this division in those three components is that you can also consider different measures to reduce the flood risk and relate those to those three components. So that's what we also did for the two districts in this project area. Is we identified a list of potential measures to reduce the hazard, the exposure, or the vulnerability, and identify which ones are most likely to be effective in this particular area. So this is let's say the long list that we considered. So what are measures that you can take to reduce the hazards? Well, the first one is to have better maintenance of ecosystems in the catchment. So essentially to maintain as much nature as possible, because then you have more area where rainfall water can infiltrate in the ground. And the second one is you can implement retention ponds where floodwater is temporarily stored. And so the water can be better be stored there than that it reaches the houses of people. And more or less the same is related to reservoirs. If you install a reservoir, that can also temporarily store water and prevent flooding downstream. And the fourth measure is that you can try to divert flow around the most vulnerable areas, especially during flood events, that part of the water will be flowing in an area where it does less damage. Number 5, you can protect the floodplains with levees or dams. Well, that speaks for itself, I think. And number 6 is you can try to create more room for the river to increase the flow capacity. Because in a lot of areas, people live very close to the river, where essentially the river has no space to flood during periods of high rainfall. And so creating more room for the river can definitely increase the flow capacity and therefore decrease the hazard. And the last option is that if you have local critical infrastructure, like very important roads or churches or schools or electricity networks, you can create some local protection, maybe perhaps a local dam to protect that particular specific critical infrastructure. Now, the second item is the exposure. You can reduce the exposure, but that's more sort of a long-term strategy. So the exposure is determined by the number of people living in the floodplains. So how can we reduce that? That is by putting restrictions on building in vulnerable floodplains. And so that's really a spatial planning issue. Related to that, you can introduce incentives to build outside the floodplains. For example, if you lower insurance costs for people living outside the floodplains and increase them for people living in the floodplains. And last is a more drastic one, relocation of homes, that's shown on the picture as well. That's very expensive, of course, and very disruptive, but still it happens in many places around the world, because if your home is in a floodplain that really floods regularly, that's even more expensive to each time try to rebuild. So that's an option as well. Now, then the third group of measures, reducing vulnerability. Now, one is, for example, elevating homes, as shown on this picture. That's a picture actually from somewhere else in Zimbabwe. And because then if a flood occurs, then only those poles get flooded and not the house itself. Similarly, you can elevate vulnerable line elements like roads and railways to prevent them from flooding. You can try to flood-proof buildings. That means that no water can enter the building, and you essentially seal them. You can also wet-proof buildings, number 4. Wet-proofing means that water will still come into the house, but if it does, the damage is far less. So that means no expensive floors and the most valuable material to put that on higher grounds. Number 5 is implementation of shelters, so that people have a place to go to during flood events. That can save a lot of lives or prevent people from getting sick from floods, for example. Number 6, flood forecasting, flood early warnings, of course, very important. If people get warned in time, they won't be surprised in their sleep, and they have time to evacuate to higher grounds. Now, related to that is number 7, evacuation planning. That means that there is actually a plan. Where should people go to? And then number 8, raising awareness. That means that you actually also communicate that very well to the people, so that everyone really knows how to act during a flood event. So these are long lists of potential measures, and in the in the study, we identified which ones are the most promising. First of all, we, Deltares, did that from a desktop study, and then some of our local partners looked into more detail with their more detailed knowledge of the area, and from that we selected the most promising event measures. Okay, now our analysis was fueled by a risk, let's say a quantitative risk analysis that we carried out, and that we will explain in more detail. So again, what we did is look at those three components: hazard, exposure, and vulnerability. So we modeled, we use models to make hazard maps. We used data to make exposure maps, and the vulnerability we looked at in different ways. And one of those ways is to create damage functions that essentially show the relation between the damage and between the flood depth and the damage. Now, all those three components will be explained in more detail in the follow-up. So I will explain a little bit about the hazard maps and hazard analysis, and then my colleague Bramka will take over and explain more about the other two components. Okay, flood hazard analysis. Well, it's a whole broad range of analysis, and I can talk hours and hours about it on all different methods that are used worldwide. But in essence, those studies come down to those 4 steps. So the first step in flood hazard analysis is that you have to identify what are the flood drivers and what causes the flood in a specific area. Now, the typical flood drivers are rainfall, high intense rainfall, and high river discharges. And in coastal areas, it's also like tides, surge, and waves. But for Zimbabwe, of course, that's not that relevant. So in Zimbabwe, it's mainly high and intense rainfall and high river discharges. Now, and then once those are identified, then the next step is to do an analysis of probabilities of those flood drivers. So what is the probability of having a rainfall of more than 50 millimeters in a day, or more than 100 millimeters in a day, or more than 60 millimeters in an hour? Those kind of probabilities are then derived in step 2, and the same for river discharge. And then the third step, in most flood risk analysis, models are created that essentially describe the behavior of the whole river catchment and its response to an intense rainfall event. And so that's often a combination of what we call a hydrological model and a hydraulic model. So hydrological models translate rainfall into river runoff, so how much of the rainfall ends up in the river. And then hydraulic models, they model what's happening in the river itself, so how does the water propagate downstream. But also, if a flood occurs, how does that water enter the floodplains, and how deep will the floodplains be flooded? That's a hydraulic model. Now, and then the last step is to combine the information of steps 2 and 3. And so we have the probabilities of the flood drivers, and we have in step 3 the response to those flood drivers. And so the combination of those two will give us the probability that a specific flood event will happen. Now, the typical result of that is shown down here. So these are resulting flood maps actually for this project. And on the lower left, you see a flood map of what you can consider to be a moderate event, that, well, still quite a flood event. So this is an estimated probability of 1 in 5. So that means a probability each year of 1 in 5 that you have such a flood event like the one shown on the left. And then on the right is a more extreme flood event of 1 in 100. So that means that it only has a probability of 1 in 100 per year that such a big flood event will occur. And then obviously, because it's a bigger event, you can see that that you have more areas being flooded, and also the color is darker blue, which indicates that the flood depth is that is much deeper than with the event on the left. So that is typically the output of flood hazard analysis, where you have a range of events with different probabilities, and you show and it shows which areas are flooded and also how deep they are flooded. Now, this is a bit of a schematic view of such a flood hazard analysis. So in this example, it's of a city that is affected by both high rainfall, high river discharges, and high seawater levels. So 3 different flood drivers, and they are all input of a hydraulic model, and that model essentially translates all possible combinations of rainfall, river discharge, and sea level into flood maps as shown on the right. And so for each potential event that you can think of, maybe high rainfall and low seawater level, or high seawater levels and high river discharges, all different combinations, you have a model that will compute, okay, which area will be flooded in such events and how deep will they be flooded. Now, and then what's in the step 2 of the previous slide, what we then need to do is to identify the probabilities of the seawater level, and that is shown here in this graph with these probability function curves in red. And so we need to derive probabilities for seawater level, for probabilities for river discharges, and probabilities of rainfall. And also we need to identify how likely is it that these occur in combination, because you can imagine if there's high rainfall on the city, there will also be high rainfall in the river catchment. So high rainfall and high river discharges are often occurring in combination. So you also need to take that into account. And then what you do is a so-called probabilistic computation. What does that mean? Well, that means that you combine the information in this graph here. So that means the information on the probabilities of the flood drivers, so the probabilities of rainfall, high river discharge, high seawater levels, and how those translate into flooding with the hydrologic model. And so the combination of these two in a probabilistic computation, that will give you probabilities of flood depth. And that in the end will result in the maps as are shown in the slides in the previous slide. Okay, so I'll end my part here and give the floor to my colleague Bramka, who will explain more about exposure and vulnerability, but perhaps to prevent also that you are listening continuously to us, this is maybe a good moment to ask if there are any questions so far on what has been explained so far.
So colleagues who are in the session, if you have any questions at the moment, you can raise your hands. If not, of course, we also have time at the end to come in.
Yeah, in the end, we will have a big discussion, but for now, this is maybe a moment for, if something was unclear, maybe you want to ask now.
You can also, of course, use the chat or the Q&A functions for any questions you may have during the session. So please use those. I don't see any hands or any questions for the moment, so maybe we can continue, and then afterwards we have time for further discussion.
Okay, Bramka, floor is yours.
Yeah, thanks, Ferdinand. Let me share my screen. So I believe you see my screen now. Please let me know otherwise. Good morning, everyone. I'm Bram Kargajavino, researcher and consultant in the field of disaster impact assessment at Deltares. And in this morning, I will explain about the concept, framework, and also application of flood impact assessment using Delft Fiat tool with an application in Chipinge and Chimanimani. Ferdinand has explained about the first part of the entire flood risk assessment, which is about the hazard. And in my presentation, I will focus on how do we evaluate or how do we translate this physical phenomenon, which is flooding, into socioeconomic impacts, and what tools are available to perform such assessment. Ferdinand already briefly mentioned all sorts of flood impacts, all sorts of socioeconomic impacts that can happen after a flooding occurs. And basically, we can classify the impacts into whether they are tangible or intangible, and whether they are direct or indirect. So basically, direct tangible impacts are impacts that we can really see by our own eyes. It is really, we can experience it and we can clearly sense it. And intangible impacts are impacts that are, well, cannot really seen by eyes, but they exist, and then they also influence our well-being when a flood hits. Where on the vertical axis we have direct and indirect impacts. So direct impacts are basically impacts that happen right away when a flooding strikes, whereas indirect impact is more cascading impacts that happens after a certain time period, after the flooding. So, for example, when we talk about buildings being damaged, roads being hit, or critical infrastructure, electricity lines being torn down, those are basically direct tangible impacts, because such impacts happen right away when a flood hits. But also because these electricity lines are being hit, because roads are being inundated, some of the roads become blocked, then it has subsequent impacts such as production losses or loss of utility services, unemployment, and even migration. So these are all indirect impacts that can also be caused by a flood. And what we are going to do now is focus on the direct impacts. So Delft Fiat, which is a flood impact assessment tool, focuses on assessing or evaluating the damages or the direct damages to buildings, and also to casualties and injuries. And also in most of flood risk or flood impact assessment project, most of the assessments focus on these two items, which are capitals being damaged, and also number of people being inundated, or even number of people being killed because of floods. These others, they are not directly covered in Delft Fiat. And what we normally do is we use a multiplication factor. So if we know the capital damage from Delft Fiat, then we assume that an extra 5 to 100% damages because of these other impacts that cannot be easily captured by using quantitative models. And now I will focus on the Delft Fiat part, and especially the damages to capital, such as buildings. This is the schematic overview of how damages are calculated. As an input, we need all these four components, which are object maps, maximum damages, water depth map or flood map, and damage functions, to come up at the end with the damage map from which we can estimate the impact of floods. I will go into each of these components in details, starting with the object maps. So when a flood hits, then what we would like to calculate is how many economic damages are there because certain buildings are being hit. And what we can use, or what we use in this project, is to understand where buildings, where the buildings are located. We use the population maps of Zimbabwe from the Facebook Connectivity Lab, and also from Kessin in Columbia University. And these population maps are a very detailed, I think it's 100-meter resolution maps, where in each cell in the map we have an estimate of how many people are living there. So if I zoom in to specific areas here, for instance, then you see the red dots, or the red very small rectangles, are basically where people live. And each of these red rectangle or red dot we have a number or an estimate of how many people are living in that area. And we use this information about population as a proxy for object maps, because it is straightforward to assume that where there are people, there are also buildings. And if there are more people living in a building, then normally the building is also a bit larger, or the area has a larger building density, which means that there will be higher damages if that area is being hit by a flood. So this is what we used in this project, the population maps. But basically, we can also use other sort of data sets. If you are interested in damages to road, for instance, then we can make use of the road network information instead of only the population maps information. If you are interested in understanding exactly the number of homesteads being flooded by 50 centimeters, for instance, then we can use the homesteads data. International development agencies are often interested in understanding the number of poor people exposed. And for that purpose, we can, for instance, use a food poverty map to estimate how many people living in food poverty are also exposed to certain flood depth. And sometimes we are also interested in understanding critical facilities such as health facilities or education facilities or stations. How many of them are being hit? How large are the damages to these facilities? Then, of course, we can use health facilities as our object maps. But for this demonstration, I go back to the previous slide. We focus on population maps, which estimates or which gives an indication of how many people are living and how expensive a certain area is as our object maps. And then this second and the third component is about the damages. So in the damage, in the maximum damage, we have to know what is the maximum potential damage in economic terms, such as in dollars or in euros, when a certain area or a certain building is being hit. And in damage functions, we will explore about how vulnerable a building is to a flood. I will go into each of these components in details. So with respect to the maximum damages, we use information from the European Commission's JRC technical reports, where this report had helped us in doing a literature review of understanding what is the maximum damage value per inhabitant in the different parts of the world. So we have an estimate for each different region. So it's different for Africa, and it's also different from Asia, from North America, Europe, and Australia and New Zealand, for instance. And the report did a literature review to understand if a person or if a building is being damaged or is being flooded, how much economic damage would it be? And we plug in this information to the population map. So here, I zoom in to one specific area in Chipinge. And then, for example, if in this one cell or in this one rectangle, we know for the population from the population map that there are 8 people living on it. And from the GRC report, we know that the average damage per person for Africa is around 11,000 USD, which means that the maximum potential damage of that cell is 88,000 USD. What it means is that if that area is completely flooded by an extreme flood depth, say 2 meters or 3 meters or 4 meters, then the economic damage would be 88,000 USD. And this economic damage is not because, and this economic damage, this estimate is because of the damages to the buildings. And we assume that if there are more people in a certain cell, then the building is either larger or there are more buildings in that area. So again, to sum up, if really this cell is being hit, then it could the damage could be as high as 88,000 US dollars. This is a big simplification, of course, because in reality, the maximum potential damage depends on what types of buildings or what types of houses people are living in. And of course, if the building, if a house on the left is being damaged, then is being hit by a flood, then the damage is likely to be higher than the house on the right, because simply it costs more money to construct a house on the right compared to constructing house on the left. So if we have a more detailed information of what types of houses are located where, then we can make, instead of using uniform damage per person of 11,000 USD, we can use a different value for the different types of buildings. So that is about the maximum potential damage. And then the next one is about the vulnerability to flood. So Ferdinand already explained this a little bit. The idea about vulnerability is actually pretty simple. Suppose this house is inundated by this much. So it is not like the entire house is being inundated or is being flooded. The economic damage would definitely be different than if the flood depth is deeper, like here in the second one. Then it is the flood depth reaches almost the beginning of the roof, which means that depending on the flood depth, the economic damage to a house would be different. And this is what is being captured by the depth damage functions, or to put it simply, the damage functions. So we also use the damage functions from GRC, where these technical reports have reviewed damage functions that are being used worldwide in different parts of the world, and make continental average damage functions for each continent in the world. And this is how a damage function normally looks like. So what you have on the x-axis here is basically the flood depth. And in this example, from 0 meter to 10 meter. And what you have on the y-axis is the damage factor, which is between 0. If there is no flood, then there is no damage, to 1, or you can also interpret it as 100%, which means that if the damage factor is 100%, then the building is completely inundated or completely destroyed. And that also means that maximum damage would occur. And what this depth damage function shows is that the damage factor really depends on the flood depth. So for example, if a house is being inundated by 6 meters here, then the damage factor would be 100%, which means that we assume that the house need to be completely rebuilt, for example. However, if the flood depth is only 2 meters, which is around here, then the damage factor is around 0.7 or 70%, which means that the economic damage to that house is not the entire value of that house, but only 70% of the total value of that house. And this is also, again, we got this information from the GRC global flood depth damage functions. And in our case study, we apply the same damage functions for everyone. And if I go back to the previous example, then of course the vulnerability to flood would be different for the different types of buildings. So for example, if these two buildings are inundated by the same amount of flood depth, say 1 meter, then it could be that the building on the left gets 90% damage, whereas the building on the right gets only 60 or 70% damage. This is not in Zimbabwe, but it's in Bangladesh, where we conducted case study. And here, for example, we have an estimation of the different types of houses, puka houses, semi-puka houses, and kacha houses. And we use different damage functions for the different types of houses. And if we have these different damage functions, so for instance, if in a certain area, the flood depth is 1 meter, and there is a puka house in that area, then the damage to that puka house is only 30%, whereas the damage to a semi-puka house will be around 60%, and the damage to a kacha house will be 80%. So if we have information about where exactly different types of buildings are being located, then we can also use different damage functions to each type of building. And then going back to this framework, then the next component is the flood depth map or the water depth map. And this is what Ferdinand has explained, where this can come from hydrodynamic or hydrological flood model. So we have a map of the flood depth in each location in our case study area. And finally, by combining these four components, the object maps, maximum damages, damage functions, water depth map, by overlaying them on top of each other, we can get the damage map. And again, here, just to give you a brief recap, we have explained about the exposure layer, which is we use the population map as our starting point, and we translate this population map into economic damage map, so the maximum potential damage. And then from the hazard layer, we know in each cell or in each location how deep is the flood. And then we also know how much damage would be incurred on a building given certain flood depth. And by combining these three information, by overlaying these three information, we can calculate the damage for each cell. If you look at this one specific cell, for example, from the population map, we know that there are 7 people living on that cell or on that area. From the hazard map, we know that that area is being flooded by 90 centimeter. And then based on our estimate of economic value, then we know 7 people translates to $80,000 US. And then from our depth damage functions, we know that 90 centimeter translate to around 36%, which means that the potential, the actual damage to that particular cell in this case is around $29,000 US. And if you look at a different cell here, we see that this cell is, or this area is located in a deeper inundation. The flood depth here is 2.2 meter, but there are less people living on it. There are only 4 people living on it. So because there are less people living on it, the maximum potential damage is lower, it's $46,000 US. However, because the flood depth is higher, then the reduction factor is also higher, which is almost 70%. And by multiplying this 46,000 and 68%, we get that the actual damage to this cell is $31,000 US. And we do the same for all cells in our case study area. So in this last example that I'm going to show you is, for instance, there are only 2 people living on it, and the flood depth is also quite low, only 20 centimeter. And this translates to an actual damage of only $2,000 US. And again, what Delft Fiat model is doing is making this calculation for all the maps or for the entire case study area. So by summarizing the actual damage over the entire area, we have the total damages of that flood event in the area. But as Ferdinand also mentioned, when we do risk assessment, we look not at only one flood map, but we look at different types of or different flood maps, those from more low impact flood to moderate flood and to more extreme or flood event. And normally each of these flood map is associated with a different probability. And this probability is basically the same like the probabilistic calculation that Ferdinand mentioned. And just to give you an example of the flood maps in Zimbabwe, in one of the I think this was in the western part of Chimanimani, then we clearly see that the flood map from a 10-year event is much more less severe compared to the flood maps of the 25-year event or the 50-year event and of the 100-year event. So what we do in Fiat is calculating the total damages from each of these flood map, which means if we have 4 flood maps, we have 4 total damages. And we do a probability calculation to aggregate the total damage from each of these 4 flood maps. And this is how we mathematically do it. So suppose in this example, we have 3 flood maps, which are flood maps from return period 10 year, 100 year, and 1000 year. So each dot here is basically the damage. And this one is the damage from 1000-year event. This one is a damage from 100-year event, and this one is a damage from 10-year event. So this is what is being outputted by Fiat. And what risk calculation means is basically calculating the area under this graph. So here we can, to calculate the area under this block, under this graph, we can divide the area into 5 different building blocks. Here, 1, 2, 3, 4, 5. And risk is basically the sum of the area of these blocks. So for example here, for this block 1, the area is basically 0.1 minus 0.01 times 10 is a rectangle. And here, for example, the damage to a 10-year event here we assume is $10 million. And then the second part is the second building block is a triangle. So we do the same calculation using triangle areas and so on and so forth. And we combine these numbers and we end up with the risks. And of course, here in this example, we assume that there is no damage below return below a 10-year event because it stops here at 10-year event. But this is not always the case. Sometimes we still have damage under a 1-year event, which means that the graph will go even further to the right. For those of you who are mathematical savvy, this is basically the idea of calculating the risk or the expected annual damage or EAD, which is the integral or the area between the different points we have from the Delft Fiat run. So to summarize, these are examples of final outputs from Delft Fiat. So after running Delft Fiat, we get risk and damages summary table. So here in this table, we know what is the damage to a 5-year event, what is the damage from a 10-year event, the damage from a 50-year, 100-year event, as well as the total risk using the formula that I showed just now. So normally for cost-benefit analysis, we focus only on the total risk. But sometimes in some applications, we would like to know what is the damage under a very extreme scenario, like a 100-year event. Then we can focus only on the damage of the 100-year event instead of looking at total risk. And in addition to this risk table, as I showed you earlier, we also have detailed, the Delft Fiat will also output detailed risk and damages map. And this risk and damages map can be used for thinking about where we should put interventions, for thinking about zoning policies. So if we know, for example, in a certain locations, there are here, for instance, there are a lot of houses located, or there are a lot of damages in flood-prone area, then we can think of how we can save this neighborhood, for instance, by making it dry-proof or wet-proof investments. But we can also do it for zoning, for making land use or zoning policies. So for example, if we know around this area there is a large flood depth, then we can make a zoning policy that we need to make sure that future urban development should not exist in this area because there is simply too much flood depth there, for example. This is also what we can do from the output of Delft Fiat. And these are some overviews of preliminary results. So we can aggregate the risk at the administrative division level. So I think this is to the different words in Chipinge and Chimanimani. And we can identify which wards are being hit the most by a flood. So here in the current situation, for example, this ward would have a damage or would have a total risk of around $160,000 to $360,000, whereas this ward has very little damage in the current situation. So this kind of map can also be used to prioritize your investment. So if you know where the hotspots of the risk, where the hotspots of the flood risk are, then you can prioritize your investments to safeguard wards that are highly exposed to such flood risk. We can also use Delft Fiat to see how risks change in the future because of climate change and socioeconomic scenarios. So what I show you here is an example, it's a preliminary result we also did for Chipinge and Chimanimani, where we assume certain population growth and also certain economic growth in 2050 based on the global SSP, the shared socioeconomic pathway scenario. And of course, because there are more people in the future, because there is economic growth, which means that the house value will also increase in the future, the flood risk will also increase in the future. And this is another example of another scenario that we run where we assume an even more extreme population growth and also an even higher economic growth, which translates to, of course, an even higher risk for the future. So using Delft Fiat, we can estimate how flood risk is now, also how flood risk would change in the future based on the different scenarios. So to recap, this is the overall scheme of Delft Fiat. What you need to provide as a user is the object maps, and for the object maps, there are already global publicly available data on population distribution, for instance, that and this global data also have good quality in most cases. You can use that global data as your object maps. But if you also have some local data, if you have some surveys of where people are living, how many buildings, how many vulnerable buildings and how many non-vulnerable buildings are in each ward, then you can also plug this information into the object maps. And then for the maximum damage also, for the maximum damage and damage functions, in this case, we also use values from or information from global reports. But if you have a better estimation of how much is the building value in Chipinge and Chimanimani, then you can plug in this information. If you have an estimation or of how much of the building will be destroyed or will be damaged given certain flood depth, then you can also modify the damage functions. And basically, these three recipients are publicly available and freely available. Whereas for the water depth maps, it's a bit trickier because then you need to know most of the globally available water depth data is not in a fine resolution. It's a very coarse resolution, but you can still use it. And what Delft Fiat does is basically combining all these four informations into damage maps and also total risk. And yeah, a little bit about the tool itself. So it is, as you see, it is a flexible framework for hazard impact assessments. It can provide detailed assessment depending on, and it is flexible in the way that if you have a very detailed population maps or object maps, then Delft Fiat can take that into account. But if your input data is quite coarse, for instance, if you only have flood maps at 500-meter resolution or 1 kilometer resolution, then Delft Fiat can take that into account. And Delft Fiat is applicable for both data scarce and data rich locations. So we have used this tool in a lot of more developing countries. And Zimbabwe is one of the examples, of course, but also in Indonesia or in Bangladesh, in Philippines, and in other developing countries. But we have also used Delft Fiat in more data-rich locations, like in the US. So for instance, in the US, we know exactly where each building is located, and we know exactly what is the value of each building. So Delft Fiat can also take that into account. And Delft Fiat can work with both raster-based and vector-based exposure data. So the example that I show you until now is basically raster-based data because we use population raster data. But in the UX example that I mentioned before, for instance, we use vector-based data because we know exactly where each building is located. How does the building footprint look like? Is it rectangle or is it trapezium and etc.? And Delft Fiat can take that into account as well. And the best thing is that Delft Fiat is open source. There are 2 versions to it. If you are familiar with Python programming, then you can use the script-based version. But if you are not entirely familiar with Python programming, then you can also use the Excel interface version where you only need to specify where you only need Microsoft Excel to run Delft Fiat instead of using Python script. If you Google for Delft Fiat, there is a web page for it, and there is the code is also available there. The instructions, the detailed instructions are available there. But I need to make a caveat that well, we still need to update the website because the Delft Fiat version that is available on the website is an older one, and we have made some detailed improvements in the newer one, but we haven't had the time to push it on the website. But you can always check the website to have a quick impression of how it works. And this will be the final section or final part of my presentation. At Deltares, we are currently exploring several advanced topics when it comes to flood risk assessment. And these topics are mainly related to equity, to fairness, to welfare, and also to cascading impacts. And we started exploring these advanced topics because we realized that not all resilience investments are created equal. So, for example, when we do flood risk planning, we are often tasked with evaluating the benefits of different measures. So, for example, here in this really hypothetical example, we have 2 different types of measure A and measure B. And then our cost engineer estimate that the cost of each measure is the same, which is 50 million US dollars. And then using Fiat, we know that measure A has benefits twice as large as measure B. So the annual risk reduction from measure A is 4 million, while the annual risk reduction for measure B is 2 million. And this is what comes out of Delft Fiat. Of course, then we will tell our clients or we will tell the governments, please invest on measure A because it has higher benefits compared to measure B. And then before the government implements the measure, they do a field visit and they realize measure A has high benefits because it is protecting richer neighborhoods. So if this fancy mansion is being damaged or is being flooded, then the economic damage would be very high. Whereas measure B has low risk because it protects slum neighborhoods. So if these slum houses are being damaged, then perhaps in economic terms, the damage is not that high. So this clearly shows how taking or using the normal approach of flood risk assessment would completely obscure the distributional impacts of flood, would completely obscure the information of who actually loses more from flood. And this is why in our recent development, we try to bring equity into considerations. So equity is basically distributional analysis of flood risk or distributional analysis of flood mitigation benefits. And we would like to take equity into account because using aggregate indicators such as total damages, total risk, obscure the unequal distribution of impacts and of benefits. And how to approach it, where we explore 2 types of analysis. The first one is explorative analysis, where we try to identify who wins and who loses under different circumstances. So what you see on the left here is the US Environmental Protection Agency last year published a report exploring to what extent disadvantaged populations such as low-income population, minority population, uneducated population are more exposed to flood compared to the average population. And last year, I also tried to develop this concept where we try to explore which word become worse off and which word becomes better off in the future, depending on different measures and also different socioeconomic and climate change scenarios. What we could also do is evaluate investments through a different lens. So the normal total risk or the total damages is basically very utilitarian, where we just aggregate or sum up the damage borne to experienced by everyone. But there are, if you look from the distributive justice literature, there are other justice principles such as the sufficientarian or prioritarian that we can operationalize to calculate flood risk. So instead of summarizing everything or summing up everything, we use different formulas to end up with the total flood risk. This is also what we now try to explore. The second part that we try to explore is about welfare impacts. And the welfare impacts is basically, well, so far we assess damages to buildings, but who really experience flood impacts are not the buildings, but the people. And people have different coping capacity and recover capacity after a flood hits. And what research has shown is that asset-based damages or asset-based risk, like what we often do, largely underestimates the human and macroeconomic cost of disasters. So we need to start moving from asset-based impacts to more welfare impacts. Within Deltares, this year we are exploring ways to propagate asset losses. So this is what Fiat normally calculates to income and consumption losses borne by each household. So we have the ambition by the end of the year that we can downscale the impacts from building level to household level. So we know exactly how much consumption and income losses are being experienced by the different households in the case study area. And the World Bank has also promoted this approach in the last couple of years. In the Unbreakable report, for instance, they emphasize that we should focus not only on asset loss, but also on well-being loss. And again, in Deltares, we are currently developing the model to perform this. And the last one is the cascading network impacts. And this is basically about the indirect impacts. So if you still remember my first slide, what I explained, there are direct impacts. So buildings being damaged are direct impacts of flood. But after the flooding, certain roads are blocked, certain bridges are being destroyed, and this causes indirect economic damages because there is a loss of productivity, there is loss of connectivity, certain areas become inaccessible, and such cascading network impacts are also important for operational planning of emergency responders because they have to know real quick where the most vulnerable populations are and where to reach those vulnerable populations. Within Deltares in the past years, we have explored this network-based model to simulate cascading impacts of disruptions because of flood. So the figure you see here is, for instance, a case study in the United States where we try to explore which part of the population cannot access health facilities, in this case, hospitals or healthcare centers. So we have a much or less rough indication of where people live. And then we also have information about the road network. And we overlay this population map with road network and also with flood maps to evaluate which roads are blocked, which hospitals are blocked, and which people cannot have access to hospital during the flood. In a separate case study in Bangladesh, I evaluate which districts are being impacted the most, not by the direct damage, but by the indirect damage of, in this case, the increase in travel time. because if a certain road is blocked, then you cannot take your usual shortest path, but you need to make a kind of detour. So if normally to access your office, it takes you 1 hour, but because certain blocks are blocked, certain roads are blocked, then it takes 1.5 hours. And we try to quantify this 30 minutes extra for each population in the western part of Bangladesh, and then aggregate it at the district level. So we know that these districts are the one that would experience the highest indirect impacts because of flood. And again, this is an example of indirect economic impacts or indirect damages that we have started to explore within Deltares. And yeah, that sums up my presentation about Delft Fiat and about the advanced topics. And I, of course, I and Ferdinand would welcome questions from you. Thank you.
So I will add 2 more slides after this, showing some more results on the study. But first, are there some clarifying questions to Bramka? There were some in the chat already. I answered them. And of course, the discussion will follow after my last 2 slides, so in 5 minutes. So then we can really discuss like ideas that you have or thoughts.
Yeah, I don't see any hands up for the moment.
Okay.
So I think we can continue.
Yes. Okay. Then so 2 more slides. Just let me make myself visible again. 2 more slides on results. Just to give you some ideas. And so in the end, one of the main outcomes of our analysis is these maps that we made. So these are 3 maps of critical infrastructure, and that relates to one of the last slides that Bramka also showed. And so there's more critical infrastructure, of course, like power networks, but these are just 3 examples. So schools, health facilities, and roads. And so essentially you want to have those accessible 365 days per year. These maps show which of these critical infrastructure are at high risk and which are at low risk. So in general, the green color here shows the areas at or the objects that are of low risk. So fortunately, with the schools and the health facilities, most of them are green, and that means that there is very low risk or low probability that they will be flooded. But of course, also you see some are orangey, which means a bit higher risk, and some are red, which is essentially the highest risk class that we identified. That means that that we anticipate that these are flooded quite regularly, and that is of course very informative, because that's means that these should probably be the main focus of taking measures. Yeah? And sometimes this can really be solved by some local measures that you can take, like protecting an individual school by building perhaps a small wall. But if a lot of them are clustered, as you see in location, you can also consider taking a bit bigger measure that protects them all at the same time. So this is just one example result, and then the next and last slide is some examples of maps that we derived in terms of expected damages. So that relates to the presentation of Bramka, where he shows like if there is a specific flood depth, then you can expect some damage, and if the flood depth increases, you can expect a higher damage. So that is shown here in this map. The main focus of this map should be on the circles. I hope you can see them. So each circle represents a homestead, so that's a small local community with some homes, and the colors of those circles indicate like how often they are flooded. And the homesteads in the area that we expect not to be flooded in these events are not shown. So it only shows homesteads with some damage. Now, the map on the left is a relatively moderate event, and the one on the right is a bigger event. You can even see that with the rivers have a darker color. That means more water is in the rivers on the right side. And so these maps really inform which wards are expected to have high damages. And again, that informs us really on, okay, where are the locations where we have most damage, and yeah, that should be the sort of the top priority to try to see if we can come up with measures that reduce the risk for those homesteads. So this just gives you a bit of a flavor of the outcomes of our of the study that we did, and that brings us, as far as I'm concerned, to the last part of today, and that is the discussion. And there were already some questions in the chat, and I answered those a little bit, but I can imagine they provoked a bit more discussion. So maybe one of the people who asked those questions would like to bring those topics up again.
Right. Maybe just before we go there, I think that's a good
Yeah.
point to retake the questions which you answered, because they're actually quite relevant in the discussion. Maybe also just to highlight, so the maps we're looking at here right now indeed is for all the types of assets, if you want. You made these maps for different return periods, as we call them, for different extreme events. So we have floods that occur every 5 years, which are moderate floods. Then we have, of course, extreme floods, which may have return periods between 500 and 1,000 years, which are extreme events, which we can relate to, for example, to cyclones or other extreme events which are not normal. In this sense, yeah, we can, of course, assess which type of infrastructure you want to secure against which type of floods. And of course, if we want to tackle the more intense floods, we need to also raise the budget for that. So there's also a question of how much resources we have available to tackle the challenge. But I think it helps to visualize what our focus could be. And just to highlight as well, of course, those maps are made into a GIS environment, and the maps and the data points for all the different infrastructure elements are also available for that reason. Just to complement to what you have been presenting. So just please, yeah, continue with the discussion then.
Yes. So are there any questions or I see someone put some in the chat. So the latest question I see, great if we can add wastewater infrastructure on the risk map as well for urban Chipinge and Chimanimani. That is a good suggestion. I think if that data is available, we can definitely do something similar as we've done for the schools. And so perhaps the person who asked this question, do they know if that information is available? Like a map with the location of those water and wastewater infrastructure?
Yeah, colleagues, I'm not the co-host, so I cannot unmute participants. So maybe if you could unmute Mark. I see also he had a question earlier in the Q&A, maybe also useful to yeah, reflect on that one.
Yeah, no, thanks very much, Koen, and also the Deltares. It's really great to see this mapping being done, and it would be great if we can indeed look at the use for some of the utilities that are managed by the local authorities just going forward, because they got heavily impacted by Cyclone Idai and the flooding. And there's some great examples where maybe we can look at reinforcing their infrastructure based on the risk mapping. So maybe we can talk with the local authorities to see if they have GIS maps available of their water and wastewater lines and reticulation systems, so that you can actually supply them maybe to Deltares or via Koen to see that we maybe yeah, get it at least highlighted. because we know that they are at risk, but we don't know to what extent the risk is really, you know, depending on the rainfall and the intensities and the frequency. Over.
Thanks, Mark, for that comment. And indeed, yeah, I think it's a question of having the data. So far, we haven't come across on that specific data set on water, let's say, production, also wastewater management. So in fact, as you say, that was heavily impacted by the cyclone. So indeed, it took them several, I wouldn't say months or, but it took a lot of time to really get back to delivering the water to the villages in around Chimanimani. So it certainly is a weakness, and we might check if indeed future flooding could be affecting the re-established lines. So that's a good estimate. Maybe if you could exchange some information with the local entities that have rebuilt the infrastructure, see if we can identify the necessary maps. And then if we have them, of course, we can relate that with Deltares and see if we can update the analysis to cover that aspect.
And to add briefly to that, I think it's important to also realize the two types of damages or impacts, the direct and the indirect impacts. So we can, on the one hand, calculate really which water supply points or which networks are being damaged, but it is a separate, a bit of a separate analysis to kind of estimate and how many people will not have access to this water supply, and that is more the indirect impacts because, well, if the water supply point is being damaged, then perhaps the entire area do not have water. But if the lines or the water lines or water pipes are being damaged, then perhaps only certain parts of the population do not have water anymore. Or perhaps because it is a network, depending on how the water pipes look like, then they can still have access, but the water has to travel to different pipes first to reach them, which means that they might still have water, but at a smaller amount compared to where it was before the flood, for example. So I think it's nice also to realize that there are these two more like really asset-based damages and more cascading damages because of the cascading impacts of network infrastructure such as water.
Okay, any other questions or like discussion topics? I saw earlier was a question about if we can include other critical infrastructure in those kind of analysis. I cannot see the question anymore in the chat. That's mainly because
it goes to answered. So you have to click on the other one which says answered. There's two questions. So if you go to the question and answer session, there is one. It says on the top you have three tabs. One is open, one is answered, and one is dismissed.
Yeah, I saw that before. Yeah, but somehow
you don't. At the bottom, I'll just next to chat. There is Q&A next to chat, between chat and participant.
Q&A. It's the Q&A. Yeah. Oh yeah. Now I see it again. Yes.
And you go to answered.
Oh yeah. That was also from Mark. So maybe Mark, was that question answered already to you, or would you like to?
No, it's
okay. Similar.
Yeah.
Thanks very much.
Yeah.
And I see we have a question from Webster and from Nito. So Webster is talking about hydromet measuring equipment. I think you answered that already. That's again a question of having the data, but it's also maybe difficult to estimate the value. And then the last part is the last question we received there was about a certain location might have few people, yet with more assets. Is it possible to factor this in our calculation of total damage?
Yeah, so that definitely is. So as long as you have the information on those assets, it can all be input. So the only reason why we used in this preliminary assessment that was shown first, we sort of assumed there was a one-to-one relation between number of people and assets. But we only use that assumption if we have no other information. Yeah? If we only have information on where the people live, then that's the best assumption we can do. But as soon as we have more information, like, hey, this is an area with more assets, more critical infrastructure, then absolutely, as soon as we have that information, we can easily include it in the analysis, and then it will automatically show that the damages will be higher there.
And,
right, and maybe just to complement, okay, go ahead, Bramke.
Yeah, also to add to Ferdinand's point, indeed, it depends on your objective, basically. So we are also doing a similar analysis for Paramaribo, and there we are concerned with the impacts to poor people. So what our team is currently doing is asking to the different resorts in Paramaribo if they have a rough estimation or a rough feeling of where do poor people live. So we have we are now collecting the data from the local officials, and we can tailor the Delft Fiat analysis to that. And if you have a kind of also rough indication of which ward has higher value assets, then we can also input that information. So I could foresee, for example, like if we have estimates of the economic total economic assets or total economic productivity or total economic output of each ward, or if not, we can also try to collect it from global data and then discuss with the local stakeholders whether these global estimates make sense. Then we have estimates for each word. We have kind of a rough indication whether one word is richer, so to speak, or has a highest value compared to other words. Then we can adjust the damage to each word instead of using similar damage per person. Then we assign higher damages per person to words which are quote unquote richer. But then if you remember my equity slide before, then the risk of doing that is that we would, well, when we implement some measures, the benefit cost analysis will look very bright because you are protecting a lot of assets. But on the other hand, there is a trade-off between this equity and also effectiveness of a measure. Then perhaps you're not really protecting the most vulnerable population. So this is kind of question that we often bumped into when we do risk analysis.
Yeah, and maybe just also to clarify that this study was kind of done with available data, and we didn't do an active, let's say, work to get additional data locally. We did the validation study, validating the work that the Deltares did locally, but I think we did not go through, we didn't have the time to really go to collect all the data and make sure that we collected data which would be useful for the Fiat analysis. So we really had to work with what we had. And of course, in future work, it's possible to target a field campaign to do more targeted field collection on some of the assets that we don't have. For example, understanding the cost for reconstructing houses and what type of houses are there. So a lot of things are possible, but in this quite quick analysis, we didn't have the opportunity to do so. So I think that's also something you need to take into account, that the project we were asked to implement only had a 10-month timeline. So we had to do everything in quite short period. I also got an interesting question from Adrian Guto, who asks, is it possible to include the flood reduction hazard options when doing scenario analysis? Say you want to know the risk reduction after construction of flood reduction ponds or flow diversing channels. Maybe a question for you, Ferdinand.
Yeah, absolutely. Now that's indeed a very good question. So that is indeed the idea or the benefits of taking this modeling approach, is that you can indeed also see what the impact is of any measure that you take, the impact on the flood risk. And you can do that for measures to reduce the hazard, exposure, and vulnerability, all in different ways. So with regard to the hazard, as the example that you have here in your question, so say you have those retention ponds, you can implement that in your model. And one of my slides before, I showed you that typically we use for the hazard analysis, we use hydrological models and hydraulic models. So you can implement that in your hydrological model. So that takes it then into account that part of the water will be stored in the retention pond, and the whole modeling chain will then in the end also show what reduction that will lead of the flooding. So if the area that is flooded decreases, or if the depth of the flooded area decreases. And so then essentially what you get is new hazard maps. And those hazard maps you can then input into that Fiat model, and you do a new run, and then you see, okay, what will then in the end be the reduction on the flood risk. So that is definitely possible. And the same is for measures that you take when you want to reduce the exposure or reduce the vulnerability. You can also implement that in the Fiat model to see what it does on the flood risk. That is, that's one of the key advantages of taking such a modeling approach, that you have those numbers available, and that you can, as much as possible, have a honest and fair comparison between the different measures. That you can show, okay, measure A leads to this reduction, and measure B leads to a different reduction of the risk.
Right, and maybe just to highlight, indeed, when we receive the maps from Fathom, which are the hazard maps at 30-meter resolution, they actually have two versions. They have a defended and an undefended version. So in fact, they do factor in flood defenses. In fact, we did not take the defended version because we thought also that the data they were using was quite global, and we didn't expect that they had the updated information on any flood defenses built in the Chimanimani and Chipinge area. But in fact, yeah, it's possible to bring those flood defenses and adaptation actions into account when doing the modeling. So that's certainly possible. But of course, again, given the time restraints, we didn't have options to really do a local assessment of where additional measures have been taken to avert a flood. So this can be seen as a worst case scenario in any case. I also saw a question from Webster. I see also you have been added to the persons able to speak. So if you want just to ask a question directly, you can just unmute and ask the question. Webster, if you're available, if you have a microphone at hand. If not, I will read your question.
He needs one moment.
Okay. If not, I will just read your question out loud. So he says that in the worst case scenario, such as recent cyclones, the rain gauges were destroyed. I was wondering what your source of rainfall data into the model you used. In a hydrological and hydraulic model we used for the same area through a 100-year return period, which coincided with the Cyclone Idai, we realized that all the indirect ways of rainfall estimation, such as satellite information, were significantly underestimating the rainfall. As a result, the depths and inundation extents were also underestimated. It's a good question. I'm not sure if you have the answer, Ferdinand, because it's more related to Fathom's work.
Yeah.
But maybe you have a response to that anyway.
So I don't have the answer for this particular study because indeed Fathom did this analysis. But in general, this is a very good point and a major point of attention in areas where there are cyclones. And as Deltares, we do a lot of projects in areas where cyclones play a significant role. For instance, we are doing currently a project in Beira, Mozambique, which of course is in the same zone when it comes to the cyclones. And cyclones really in a flood hazard analysis deserve a separate approach compared to, let's say, normal rainfall events. So that's also often how we treat them. And the reason is that of, let's say, regular rainfall events, you typically have enough data available because maybe you're lucky, you have 40 years or 50 years of rainfall information, and that typically already says a lot. But with cyclones, that's a different story because they are often quite rare, and each cyclone is a very unique event. And of course it makes a big difference if the cyclone goes right over your area, or if it's just 100 kilometers north or south. So yeah, if you have the resources available to do a really comprehensive flood hazard analysis, and that, let's say in studies where we have that, we really do a separate modeling approach for cyclones, where we take into account as much as possible different scenarios of cyclone tracks, also with the likelihood, and indeed account for the fact that with cyclones you have typically much more rainfall than with average events. And then yeah, you can take that different behavior into account, but regardless, it's a challenge anyway. Cyclones, it makes flood hazard analysis definitely more challenging.
Yeah, also just to complement that, in fact, the rainfall data from the actual cyclone is also very spotty. I think the most stations were destroyed during the cyclone, and the data that they do have is not very, let's say, there is also challenges with the quality of that data that they did collect. So the actual measurements are very scarce, and in this sense I think it's also challenging to say let's move now to real measurements when they're actually not available. So I think in some way we need to use what is available. In this case it's mostly indirect measurements, which we know have their own biases and errors to it. So that's reality. Webster, do you want to come in? I see you're unmuted.
Yeah, yes, sorry, my network has been bad, but I was following, and because the challenges that we have in most of our flooded places here in Zimbabwe and basically in Southern Africa is that there are a lot of these cyclone-induced flooding events. So like I mentioned on the message, that's the challenge that we have been having with the models that we have been using, that they've not been able to really track all the inundation extent and all the depth. But I'm sure the answer that has been given is satisfactory, to say that we need to go maybe another step further and reconsider maybe the available modeling too. Maybe my last remark, if not question, is on whether this model is available for teaching and research in our institutions here. Thank you.
And which model do you mean? Like the whole model, or just the Fiat model, or also the hazard model?
Maybe we can refer to both, and I can maybe start with the one that we used for the hazard maps, which is not managed by Deltares. So in fact, those currently are not available as models. We tried to see if they could made them available, but unfortunately the setup of the entity that is providing those maps is to be setting up a license, so they're not really able to provide those models to any teaching and engagement. So I think that's a bit of a limitation that we face. We're currently looking at other options for future work, but to be honest, we're currently using the fact that this is a very good model, very well established, and it's been used globally. So that's also an opportunity. So in this sense, yeah, we're open to explore other options, but we do value the high quality of the work that Fathom has been providing and the availability in the areas we need it for. And maybe you can refer to the work that Deltares is doing on the Fiat itself.
Yes, well, maybe Bramke also wants to comment on it, but so Fiat is definitely, we're open about other people using it. As a teaching tool, that would probably provide, let's say, a very slick user interface. That's not what Fiat is. So it's really a number crunching tool. But if people have time to invest in that, students as well, then it's open for use, for sure.
All right, thank you so much. And of course, it can maybe be demonstrated using some of the case studies that are part of the currently available model, just to give the insight how it works, not necessarily transferring the tool, but just saying how you approach such a risk assessment. Okay, any further questions? I see Taka asked for the presentation, so we will, of course, share that as well as the video of this session. So that's not an issue. Any other questions? You can also raise your hand or unmute. I don't see any further questions. So yeah, maybe going a bit back to the final questions. We have a few minutes left. So I think we went through how the results can be used in Chipinge and Chimanimani. I think that was extensively discussed today. Also, what are the limitations? I think we mentioned several of them. Limitations is basically limited to a lack of knowledge on detailed information, which of course, if more time and funding is available, that can be collected. But it's of course, for large areas, it always will be a challenge, and some kind of abstraction is always going to be necessary. And then, of course, for follow-up activities, we're also exploring to upscale this work to the larger Bupusa area, the Buzis, Save, and Pungwe River basins between Zimbabwe and Mozambique. And we'll have a special session on that next week on Tuesday, where we explore further how we can upscale the work from this specific project towards the larger transboundary basins. So we just, we didn't have much discussion on that today, but I think there is potential for doing so. Again, data collection will be key. And of course, we can do a very rough assessment using global data sets, but again, making sure we have the most accurate data available for those areas will be key to make it a more meaningful and impactful analysis. Any further comments on that last point? Or any other comments you would like to make before we start finalizing this session? As I said, you can just raise your hand or unmute. I don't see any further questions. All right. If no more questions, then I just would like to thank the presenters at Deltares specifically for providing us this insight in how to use risk assessment. And I think also thanks Bramka for elaborating on these additional elements that you mentioned, the fairness of the analyses, the equity, which I think also come up when you talk about climate change adaptation again, and that's also where your specialty lies, that when you look at the adaptation actions, if you don't look at equity, you might look at the wrong indicators. You might look at economical indicators, which might be very unfair for many people who do not have direct contribution to economical output in some cases. So I think it's a very important element which we haven't explored in this analysis, and might be relevant for future work that we would like to engage in going forward. So I think on behalf of everybody who was listening here today, and also the participants who might tune in later on the recorded session, I would like to thank Deltares for the work done. And maybe if you have some final comments from your end before we finalize, then please go ahead.
Well, first of all, thank you very much, Koen, for this opportunity, and thanks to the audience for participating. It was a pleasure for us, and I hope that what we brought today can be helpful for you. And who knows, we will meet again in the near future.
All right, Bramke, anything from your end?
Yeah, also thanks a lot for the opportunity and for all the participants. I hope we both knew useful today, and looking forward to collaborate further.
All right, and I just then finalize thanking the donors, both the World Bank and UNOPS, for giving us the opportunity as well to work with Deltares and the other teams to make these maps available and to make a methodology which can be upscaled to other areas. So in this case, thanks a lot for that support, and I hope we can also further upscale and provide sustainability to this approach in other areas of Zimbabwe and in other areas in Southern Africa. So thank you so much to all for attending this interesting webinar, and I hope we can continue working in this field all together. Thank you. Have a good Friday and a good weekend.
Yes. Thank you all.
Thanks.